Namaskar, Swaroop. Good morning.
Sir, good morning.
So welcome back. So we should welcome Professor Siba Kumar Udgata for our second session. And he will speak on a topic which is, you can now relate to the first one, sensing without sensors, human activity recognition using Wi-Fi signal intelligence. As you know, he is a very good academician, researcher, as well as speaker. So I think all of you will definitely enjoy his lecture and will learn lot of things. So let me just give a small introduction about Professor Udgata. Mm, uh, he is a professor in the School of Computer and Information Sciences, University of Hyderabad, Institute of Eminence. He served Center for Modeling, Simulation and Design as a director between year 2012 to 2016. He was a United Nations Fellow and worked in the United Nations University and International Institute for Software Technology, Macau, as a research fellow in the year 2001. His research focus is on intelligent algorithms for wireless communication, mobile computing, sensor network, and applications. He has worked as principal investigator in many funded research projects in collaboration with Stanford University, University of California, IIT Delhi, and few others. He has published research papers extensively in many peer-reviewed international journals and conferences. Now, sir, over to you. Please tell. Thank you.
Thank you, madam. Thanks for a small and nice introduction. I thank the North Odisha University Administration and Department of Computer Application in particular for organizing such a wonderful week-long FTP and also for inviting me to share our experience. Okay, I also listened to almost all the talks in the last 2 days and today's morning session also. I must say that the speakers, am I audible, right?
Yes, sir, absolutely.
So the speakers have covered almost all the areas of artificial intelligence, machine learning, applications of artificial intelligence, machine learning, and all that. Now, pardon me, because it's also an experience for all of us, because I'm also not used to speak to an audience just sitting before a laptop and then emulating myself as if I'm speaking to a group of hundreds of students or participants and all that. And we feel, it's an experience for us also, as my vice chancellor here at University of Hyderabad says that challenging times requires challenging ideas. So we are also trying to figure out what are the possibility best alternates so that we can try out and see what best we can deliver at this point of time. Now, the whole idea of this talk is, as Madam rightly pointed out, that it's an addendum or it's an extension of what Dr. Tinku Acharya has just mentioned. It's a wonderful talk actually. It's a wonderful presentation, and I would like to match it only, and I hope that I will not bore you. So let me share the slides for some time, and then just a minute. Yeah. So I think these slides are visible to everybody, right?
Yes, sir.
No,
Yes,
sir.
yes. It's visible.
Is it? No.
It's visible. Please.
Okay.
Yes, sir. Visible.
Visible. Okay. So, madam, you can check it also.
Yes,
So let me continue with the slides. Actually, they say the title is Sensing Without Sensors. In fact, just 2 years back, I watched a video of a Microsoft lecture series where the professor from Stanford University gave a talk on sensing without sensors. And that was slightly in a different context. But here I choose that because we are not using traditional sensors for sensing. And what you do, you will try to detect. I mean, Dr. Tinku Acharya was also mentioning how do you detect human activities, how do you detect crowd behavior. So in this case, we will also try to detect a particular human activity using Wi-Fi signals. So Wi-Fi signals are traditionally or till today are being used for data communication. Now, but it has many more potential to explore. So Wi-Fi signals are omnipresent, and we can explore that signals. And how do we explore these signals and try to find out many other activities apart from data communication? Data communication is anywhere there. So I work for School of Computer and Information Sciences at University of Hyderabad, and very recently we have been conferred with the status of an Institute of Eminence, and it's a Government of India status, and we look forward to use this funding and use this status to excel ourselves. We are already doing good, but we want to excel further also. Now, let's say what is sensor-based sensing, and this is sensor without sensing. So a sensor, as we all know, and I quote Wikipedia here, that a sensor is a converter that measures a physical quantity and converts it into a signal which can be read by an electronic instrument, mostly an electronic instrument. And all your sensors, your temperature sensor, your glucometer sensor, your video camera sensors, your thermal sensors, so everything is a sensor. The point here is that it measures that particular physical quantity and converts it into a signal. It doesn't convert it to a number. It doesn't convert it to 25 degrees centigrade or 30 degrees centigrade. It converts it to a signal, and based on the change of the signal, we map it to a number. And that's what a normal traditional sensor does. So the second definition is a little more elaborative. So it says that a sensor is a device which responds to an input quantity, let's say a temperature or a pressure or a humidity, by generating a functionally related output. What I mean by functionally related output, let's say it generates a voltage, or it can generate a current also. So if it generates a voltage, now with 25 degrees centigrade, suppose it generates a voltage of 2.5 millivolt. With 30 degrees centigrade, it will generate a voltage of 3 millivolt. So it's a functionally related output, may not be necessarily linear. I repeat it, it may not be necessarily linear, but it's a function. Now the function can be a nonlinear function also. So usually in the form of an electrical or optical signal. So if it's an optical sensor, it's an optical signal. If it's an electrical sensor, it can be a voltage or a current. Now a sensor's sensitivity indicates how much the sensor's output changes when the measured quantity changes. That's what we call in physics least count. So suppose the temperature changes from 25 degrees centigrade to 25.1 degrees centigrade. What is the change in the voltage measurement or current measurement or light intensity measurement if it's an optical sensor? So based on that, the quality of sensor is determined, the cost of sensor is determined, the usability of the sensor is also determined. So there are three things which I want to say. A sensor-based sensing is basically, it is a sensor designed for a particular purpose, for example, pressure or temperature or humidity or whatever. Now, for that purpose, the sensor will measure that particular physical phenomena and convert it to a particular electrical or optical signal, which will be mapped onto a number. So that's what a normal sensor does. Now, sensing without sensor is that we feel that, okay, we will not be using a normal sensor or made or modeled for a particular activity or for a particular physical quantity measurement. We will try to see what we can do without sensors. So, for example, this Wi-Fi signal, I will be talking on this only. Wi-Fi signal is omnipresent, but it's designed for data communication. Now, can we do that? Can we use that signal, apply some artificial intelligence technique, apply some machine learning technique, and try to find out that with that what else we can do? So that is the purpose of this talk. So I think the sensor-based activity recognition, the title of the talk was human activity recognition. What is human activity? Jumping, running, clapping, crying, laughing, falling. So these are all activities. Even the kids do all these things in the crèche and all that. So the sensor-based activity recognition people have been doing, are doing, and will also continue to do it. So how they do it actually? They use sensors. So what are the sensors? They're accelerometer sensor. What is an accelerometer sensor? The accelerometer sensor gives you or measures the change in the x-axis, y-axis, and z-axis. Suppose I wear an accelerometer sensor in my hand, and the hand moves in all possible directions, then it will give me some values which will measure the change in the x-axis, the change in the y-axis, and the change in the z-axis. Or that has been traditionally used for activity recognition because any activity will require some kind of a movement, and the movement in x, y, z direction can lead to a recognition of an activity. What is a gyroscope sensor? Gyroscope sensor is the change in the angle. Suppose you rotate your angle of your hand or something. For example, you want to touch your face. So you rotate your hand, the palm comes to the forefront, and then you touch your face. So gyroscope sensors are theta, angle. Accelerometer sensor, XYZ. Camera sensor, I think I don't need any introduction. Tinku Acharya has given an elaborate way of detecting human activities based on camera sensor. So if there are cameras, you capture the images, you capture the videos, and then do analytics, run analytics on that to determine various types of human activities. That's a thing of past now. Tinku Acharya has done it marvelously. Wearable sensors, I think all wearable sensor in the sense the sensors which I wear in my body. For example, camera sensor, you don't wear it in your body. It is from a distance. The camera is at a distance, and remotely it monitors you. What is wearable sensor? Wearable sensor means you wear it in your body. Now, all these things, all these sensors are basically, when you do an activity recognition system, Tinku didn't tell us very explicitly, but they are mostly cloud or server-based analysis. For example, you get a huge amount of data. For example, camera or video, they are huge. The amount of data is huge. Computation is huge. Requirement is huge. And then you transfer it to a cloud or a server, and the server there, they do all the analysis. So what is the conclusion from this? We have lot of such devices. We have smartwatch, we have Fitbit-like devices, we have smartphones. So your phone, everybody's phone, there are almost 50 sensors. It has accelerometer sensor, it has a gyroscope sensor. So people have worked on smartphone-based activity recognition. N number of papers have been written on that. Now, so all these things are there. The sensor-based activity recognition is there. It is going to be there because, as Tinku pointed out, and as we all know, that the accuracy level is still a challenge, and the false positives are still a challenge, and we need to continuously work on it to improve the performance of the system. Now, what are the major challenges with these kind of technologies? I think I don't want to say that they don't have their uses, but there are certain challenges. For example, these devices are not very convenient to use. For example, if I have to wear something I have to wear a jacket, or you have to wear a, say, for example, I purchased a Fitbit, but many a times I forget to wear it whenever I want to go for a walk. Because long time back, I have stopped using watches, and I don't like wearing something. So even I don't like to wear a watch actually. So forget about a big device, or if it is a slightly heavier device, then it's not very convenient to use. And there are many places I don't want to wear it and sleep. So many times people say that I'm not able to sleep if something is tied to my body or something. I don't want to go to restrooms with wearing a device and other things. So all these issues are there. So it's not very convenient to use. Acceptability of the devices. Many people have their own perceptions about these devices. Some people say that, oh, this must be tracking my body. This is radiating some signals which I may get used to cancer, or I may get something else. It affects my mental capacity. It creates irritation. So many people have so many ideas. For example, we have been working with a project, and in that project, I think we wanted to monitor the baby health when the baby is inside the womb of the body before it is born. Now, ladies didn't accept it. They don't want that. They thought that, okay, it will affect the baby in some other way and all that. So they kind of refused it. So acceptability of wearable devices is a big problem, particularly in a country like India. Now, affordability, that's also another thing. Many times this cost is prohibitive. I think Tinku didn't elaborately tell that the cost involved in all these things. And I tell you that these are all very costly things actually. The analytics, the cameras and all these things are very, very costly. For example, he showed a video where it shows that it can monitor the temperature of the body. But let me tell you, the temperature, the thermal sensors, the thermal cameras, which can measure a hot body from a distance, is cost around 5 lakh to somewhere between 20 lakhs. So these are all very costly devices. So many times they are not affordable also. Availability. Now, suppose we want in a country like India, we want some 100 crore things. Is it available? So large scale availability is also a challenge, and they are not there. And most importantly, I come back to that, the privacy. Camera and other such devices are considered to be a breach of privacy. Now, suppose I want to monitor somebody, my parent or grandparent is there, and they are in the restroom and they may fall down or something. Can you fit a camera in the restroom? No. So there are certain cases, there are certain use cases where camera cannot be used because of privacy issues, because of other considered issues. So we have to look at some other option In addition to this, of course, camera has its own uses, video has its own uses. Now we look at some other options, whether we can use some other options where a camera cannot be used, but still we want to make use of a image kind of a stuff. So the challenge here is to develop a system which is acceptable, the first thing, which is available in the sense it is possible. I mean, I can get it if I need, and it is also affordable. So that's the challenge where people started working, that we have to find out a technology which is acceptable, which is available, and which is also affordable. Now, coming back to the technology part, what is Wi-Fi sensing? I'll tell you, we use this word called Wi-Fi sensing, but you know, Wi-Fi is not sensing. Wi-Fi is actually for communication, Wi-Fi communication. So many people know that Wi-Fi is used for communication, but Wi-Fi sensing is a recently coming up area where people start or think of using Wi-Fi. And I tell you, there are very few groups actually. One group in MIT, USA, another group in Washington, and another group in Australian University. These are the three groups which are actually engaged in Wi-Fi sensing research. Others, I mean, like us only, they try to try their hands and all these things, but majority of the research comes from MIT, USA. So what is the idea? Can Wi-Fi signals be used for sensing purpose? That's the first question. And the answer to this question is a big yes. Yes, Wi-Fi signals can be used for sensing purpose. The idea is that the physical layer capability of Wi-Fi signal, you know, in the network layer, there is a physical layer, and in the physical layer has made it possible to reuse the Wi-Fi signal for both communication and sensing. And till now, mostly, we find that communication is the 99% application of the Wi-Fi routers, but now we try to look at for this sensing. Now, sensing via Wi-Fi would enable remote sensing without durable sensors. So that's another. So here, what we are trying to do, we don't want to wear anything because I am not comfortable with that. So sensing via Wi-Fi would enable remote sensing without some kind of a durable sensor. I don't want to wear an accelerometer. I don't want to wear a gyroscope. I don't want to be surveilled. There should not be camera surveillance. So due to the popularity of Wi-Fi devices, and then look at this, Wi-Fi is almost omnipresent. It's available everywhere. So you don't have to tell that whether it is available, whether it is affordable or not. Every household, at least for this pandemic situation, every household, every thing is there in the a Wi-Fi device is already there. A router is there. Even your cell phone towers, they are also Wi-Fi signals. So all these things are there, and they are kind of ubiquitous. Now, what we are trying to do, one of the world's largest wireless sensor network. If you say that Wi-Fi can become a sensor, then it becomes a world's largest sensor network. And despite increasing research interest, wireless sensing is still in its infancy. There is a lot of work to be done. So what we try to do is that we'll try to present in this particular talk that what is the feasibility and limitations of the wireless, sensorless, and contactless sensing via Wi-Fi. So what is that we are aiming at? We are aiming at it should be wireless. There should not be wires attached to my body. It should be sensorless. I don't want to put sensors across my body. And it should be contactless. Nobody should come touch me and all these things. So if these three can be achieved, and Wi-Fi is a suitable candidate for that. So what is Wi-Fi sensing? I'll continue to talk about it and just listen to it, and after that it's slightly more interesting. So the Wi-Fi sensing is a new technology that enables motion detection. It can enable a movement inside a room and all these things. It can enable also gesture recognition. For example, you raise your hands and say that you get out from this place. So the way I gesture it, right? The way the body parts move and all these things, that also the Wi-Fi sensing, Wi-Fi can recognize it. And many people, very recently, into 2020 April only, people also say that there are even biometric measurements are possible using Wi-Fi signal, in the sense that you can measure the heartbeat, you can measure the way a person walks. So there are certain biometric signatures. The way I walk, the way I breathe, the way I speak, and all those things can be combined to identify a particular human being. That's also very recently people have started working. I think I saw only one paper that came out in April 2020. Now there are other technologies also, say radar signals actually, like video-based. I think Dr. Tinku Acharya has already said that. So video-based radar, people are using in defense and all these things, but they're very costly and they have their own issues. So Wi-Fi has become a suitable solution because of its bandwidth, because of its coverage. It's there in every home, every place and all these things. Because of its penetration, it's there even in the villages and all that, and also the transmission power. Now look at this, how it is done. I'll just list out some 3-4 points here, and then we'll discuss it in elaborate mode. So at least one Wi-Fi transmitter and receiver are needed for sensing. So what do you do here? I mean, you may read it, but just listen to me for a few seconds, at least for 1 minute. Let's say I have two Wi-Fi devices. One is a transmitter and one is a receiver. Now imagine that you have a Wi-Fi transmitter at one corner of the room and you have a Wi-Fi receiver at the another corner of the room. So what do? The transmitter will transmit the signal, the receiver will receive the signal. Now the receiver should be able to sense the changes in the transmitted signal. So what happens is that suppose let me assume that in the room where I'm working now, I'm presenting. So there is nobody there except I am there. Now let's say there is a transmitter Wi-Fi router and there is a receiver Wi-Fi router. So the transmitter sends the signal, the receiver receives the signal. Now you receive the signal and say this is the null case, this is the ground truth. There is nothing else inside the room. Now the moment somebody enters, let's say my daughter or my wife, somebody enters into the room. Now there will be Wi-Fi signals. I mean, these are all waves, right? So the waves will hit his or her body and then it will start reflecting, and then the multipath fading and all these things will happen. And the receiver will sense that change in the signal. So change in the signal means there will be delay in receiving it because there is a reflections, there is a noise will be there. So now I say that look, this change in the signal characteristics is due to my daughter entered into this room. Now if I tag this, that this change is because my daughter entered into this room, this change because a dog entered into this room, this change because there is somebody fallen inside the room. Because when you fall, some changes will happen in the Wi-Fi signal because the reflection pattern, the fading pattern, and the delay that happens, so everything will change actually. Now if I can look at those things and characterize those things, train those things, and then the receiver, depending on the receiver pattern, the Wi-Fi signal pattern at the receiver end, can characterize what is happening inside the room. And that's technically at the abstract level, that's the key, that a Wi-Fi transmitter will transmit the signal, a receiver will receive the signal. If something happens between the transmitter and the receiver, there will be a change in the signal characteristics. If the signal characteristics change can be captured, trained, learned, and then you can deploy it and then find out that what is happening. So initially the system learns the environment without no humans in it. I told you that nobody there inside this room now. Now whenever the system wants to track or sense the human, the transmitter sends the signal to the receiver. The receiver receives all the reflected and refracted signals from the objects and the humans along with the transmitted signals from the transmitter. So the transmitter, we don't get only the signal, we get all the reflected signals, we get all the refracted signals, we get all the delays. So all these things can be captured and then we can train it. Now we'll see some of these experiments. So this is a figure, but that's what I have already explained. So there is a radio. If you look at the bottom part of it, let me activate a laser pointer there. Okay, so if you look at the bottom part of it, there is a radio signal that is coming out, and this is Wi-Fi. There is also a Wi-Fi here. So this is the environment. One fellow will start sending. This is the transmitter, and this is the receiver. Now once this happens, then what you do, the existing Wi-Fi services, you have all these things are there. Now what you do, the Wi-Fi sensing agent will have algorithms. I call it the machine learning algorithms, AI algorithms, and all these things. And based on these algorithms, you decide what application you want to deploy. Whether you want to deploy to detect somebody, whether he has fallen, whether you want to deploy somebody who is a trespasser. So all these things. And as I told you in the latest paper, even they are trying to detect the heartbeat rate, the respiration rate of a particular person. So all these things are possible, but you require a lot of training, a lot of data on that. Now the variants in Wi-Fi sensing, what are the different variants? There are normally called as two types of sensing. One is called active sensing and another is called passive sensing. Now let me start with the passive sensing. In the passive sensing, you don't have to do anything. There is a Wi-Fi router in your home or your office. It is sitting there. It is continuously doing the data transmission and all these things. But at the same time, for example, the Wi-Fi sensing utilizes the transmission as part of the regular Wi-Fi communication. The Wi-Fi sensing receiver rely only on the transmission between itself and the transmitting device. It doesn't do anything else. So it's in a passive mode. The data communication is happening, that is going on, and somebody is watching, sitting in a passive mode. And if there is some disturbance in the signal pattern, that disturbance will be characterized as what kind of disturbance it is, and you try to sense it. What is active sensing? You take a transmitter with you. So and go to a particular person, send a signal and receive it back, and then study the characteristics of the signal. So the active sensing is that you have to initiate it. So who initiates it? In the passive sensing, the Wi-Fi router is sitting quietly doing its job. You come in and observe the signal pattern and then decide what is going to do. In active sensing, you are an active agent here. So the active agent here is that the sensing device triggers for the transmission of the signal for the purpose of Wi-Fi sensing. Now I want to go to, I want to see that whether there is a dog inside this room or not. So I come out from outside, I send a Wi-Fi signal transmitter, then this signal comes back, and then I try to characterize the signal and try to see that what kind of animal it is. So this is called active signal. So classification, like what is there in the Wi-Fi signal, what are the characteristics of the Wi-Fi signal, so that you can use this for training and for sensing. There are three major characteristics. One is called received signal strength indicator. I think almost all whosoever uses a smartphone is aware of this term, because in every mobile phone or in smartphone you see that what is the signal strength. We see 5 vertical bars, 3 vertical bars, 2 vertical bars, and you look at it and say that the signal strength is not good. So the received signal strength is that what is the strength of the received signal from the Wi-Fi router or the Wi-Fi host there, which is sending it. So that any device can measure it easily. There are almost everywhere it is there, omnipresent. So the received signal strength is one indicator of a Wi-Fi signal, one characteristic of a Wi-Fi signal. The second characteristic is known as channel state information, CSI. Now, I don't want to go back to this communication engineering part, but let's say channel state information. Every Wi-Fi signal, depending upon the bandwidth, they are divided into many sub-carriers, sub-channels. Now, each channel has a characteristics. Characteristics means what is its strength, what is its modulation, and all that stuff. So the channel state information, I will come back to that. So every Wi-Fi signal consists of a channel state information called. Okay, so every Wi-Fi signal has a channel state information. So the channel state information, or we call them as the CSI values. Now, what is a CSI value? CSI value is a number, but the number denotes what is the modulation, what is the strength of the signal, what is the delay in transmission, and everything. It's a composite number. What is Wi-Fi radar? Wi-Fi radar is that you decide what is the bandwidth you want to send the signal. You define at which power you want to send the signal, transmitting power, etc. So that's a Wi-Fi radar, and for which we use software-defined radio. But the software-defined radio means you decide the bandwidth, you decide the transmitting power, you decide the compression technique used. So everything you decide, you code it. But the first two, what I said, received signal strength and channel state information, are prevalent with, or it's already present with the standard Wi-Fi routers. You don't have to do anything there. Now, Wi-Fi radar needs extra devices, which increases the cost, so we are not looking at that. What we are looking at is the RSSI, that means received signal strength, and channel state information, that is the CSI, are device free. You don't have to create any other device, because the Wi-Fi signal will come, hit my body and go back, right? And when it hits my body and goes back, the RSSI value changes, the CSI value changes, and based on that, we try to see what else we can do or what else information we can find it out. So sensor-based network performance is subject to several constraints such as limited energy, onboard computation power. So though many things are there required on the sensor board. This Wi-Fi technology has a strong potential in indoor as well as outdoor sensing application. For example, in indoor, your video things, camera things doesn't work. Okay, so in the indoor, our video things and the camera things doesn't work much, because you don't want cameras, video cameras, etc. to be fitted in my drawing room, in my bedroom and all that. So Wi-Fi technology has a strong potential candidate there. Existing Wi-Fi infrastructure also provides similar opportunities. So we don't have to think of a different kind of a Wi-Fi infrastructure, but existing Wi-Fi infrastructure also can be used. Wireless signals can be utilized not only as a communication medium to transmit data, I have been repeatedly telling it, but also as an enabling tool for realizing the non-intrusive device-free sensing. Non-intrusive means you don't have to come and pierce in my, for example, in blood sugar. You come and put a needle inside. So it is non-intrusive. You don't have to. The body is not getting intruded by any outside device. It's a device-free. I don't want to wear anything. No jacket, no watch, nothing. So it's a device-free sensing. We call it popularly known as a DFS, and non-intrusive. Now, look at this. So Wi-Fi signals, people have done it, and we have also done some experiment which I will share with you. Wi-Fi signal now has been widely leveraged for various sensing tasks such as localization, where a particular person is through Wi-Fi signal, no camera, no nothing else. people counting, how many people are there inside a particular room. That also people have used using Wi-Fi sensing. So you have a Wi-Fi router inside your conference hall or meeting room, and then you can also count how many people are there inside the particular room. Now, this device-free wireless sensing (DFWS) does not require a person to carry or equip with any kind of device. So the person, say you ask somebody that you take it, you wear it. Many people feel it is uncomfortable, right? Suppose somebody is coming into the meeting room and you say that you have to tie it in your chest and you to wear it. They may not like it. So it is nothing. You don't have to ask for any cooperation there. Now, compared with other state-of-the-art sensing techniques such as camera and wearable sensors, DFWS does not require specially deployed sensing techniques. It can also, that's another important point. I want to highlight this point. It also can work in dark and dusty environment. For example, in a low illumination, the camera doesn't work. In a dusty environment, the camera doesn't work, or the sensors do not work. But Wi-Fi doesn't depend on the camera. I mean, the light conditions. It can work in dark. It can work in dusty environment. So that's a immediate advantage of Wi-Fi sensing. So how do we do it? I mean, let me go through it. I mean, it's not a very difficult thing. A person within the effective area of wireless, because the person who is going to be monitored has to be there within the Wi-Fi zone. Otherwise, I mean, if he is not accessible to the Wi-Fi signals, then there is no point in doing all these things. So a person within the effective area of a wireless network influences the propagation of wireless signals. By analyzing the wireless signal pattern and characteristics, it is feasible to predict the state of that object or that person. For example, motion sensing can be achieved by observing the Wi-Fi radio signal strength and its fluctuations. I have been repeatedly telling it actually. Now, however, the propagation characteristics of wireless signals are extremely complex. I don't want to say that it is easy and anybody can do it at any point of time. This is definitely complex, but it is also challenging to develop a perfect mathematical model. That's the challenge here actually. So, let me kind of conclude the whatever so far discussions. Wi-Fi based system use the variations in the wireless channel to track people in a given environment. Existing systems can be grouped into three main categories. One is called the received signal strength based sensing, CSI based sensing, Wi-Fi radar based sensing, that is the software defined radio, and time of flight based sensing. What is time of flight? When you send a signal, it will take some time to come back actually. Now, if there are so many reflections, so many objects inside that, there will be a lot of reflections, etc., and it will delay the process. Now, if it delays the process, then the time of flight means it will travel and then come back, the round trip time, or we call them RTT. So the round trip time also gives you an indication that there is some object inside the room or inside the region of interest. That's it. So RSSI and CSI device are device free and does not require any more extra installation. Now let me come down to a small part of the. So, but the problem with RSSI is that it's only a signal strength. It doesn't give you any other information. So it's very coarse-grained information. It doesn't give me all sorts of information which I need for particularly classifying or recognizing the activities. But at the same time, it gives me some information. So this could also be viewed as the sum of strength. So for example, I told you also in one of the previous slide, the Wi-Fi actually consists of 30 subcarriers. It depends on 5G or 6G or 4G, etc. But at least on an average, it consists of 30 subcarriers. That means you are actually transmitting the data using 30 sub-channels. You are using one channel, but the channel is divided into 30 sub-channels. I think I don't want to go into those details. OFDM and all these things are there. But let's say there are 30 sub-channels or sub-carriers in one channel through which the information goes. Now, the RSS, that means the signal strength, is a combination of all these 30 channels and then taken the average actually. So it doesn't give me a lot of information about the characteristics of the channel, and so it has its limited applications. So when a person moves, multipath changes. I'm looking at the last paragraph. When a person moves, multipaths change and RSSI value seems to be fluctuating and may not give enough information for activity recognition, but it gives some information. Now let's say we did some experiment in our school actually, in our university, and other people have also done it, but we also wanted to test it actually. So what we did actually, if you look at this, look at the figure actually, there is a RX is a receiver, and there is a transmitter. So at the one end of the room we have a transmitter, a simple Wi-Fi router. At the other end of the room we have a receiver, and there are some people around it. So what happens, the multipath is that you look at this, the signal goes like this. The signal is 360 degree, right? It goes in all directions. So the signal, the Wi-Fi signal which goes in this direction hits this body and then goes here. the Wi-Fi signal which goes in this direction will hit this body and go here. The Wi-Fi signal which goes in this direction will hit this body and go here. Now this, so the receiver there will get a signal, the RSSI value, and that RSSI value is a combination of all these reflections, multipath components, delays, and everything. Now, if you put them all together and then try to characterize how many people are there in this room. So what we did, so this is I think a simple model actually. I think people who are working on IoT and all that, this ESP8266 module is a very common module actually. It doesn't cost even 700 to 800 rupees. So it has its, so initially we set up a Wi-Fi ESP8266 module for collection of the RSSI value. So we collected the RSSI value for people counting. 2 ESP82. What is 2? 2 means one for transmitter, one for the receiver. And experiments are conducted using 5 people walking through the communication area inside the room, and then the data collected with a sampling rate of 500 milliseconds. So we collected the data at a rate of every 500 milliseconds. We collected the data for around 8 minutes. So I think this is what the specification actually of the ESP8266 module. It's a 32-bit module. So the voltage is, operating voltage is 3.3 volt, and all those things are written there. Now look at this. So what we did, let me again explain the experiment. There are 5 people. The 5 people are coming into the inside room and moving inside this room and then leaving actually. So when they come inside, they stay and then they move, and they go out, and again coming, again go out. So we collected the data for 8 minutes, and the data is collected at an interval of 500 milliseconds. So that means per second, two data we collected it. Now we just plotted this. Look at this. In the y-axis we plotted the received signal strength, and in the x-axis the time made there. So if you look at this, so experiment is conducted around for around 8 minutes with the 5 people walking through the communication area, entering and exiting one by one with an interval of 30 seconds. They come and then exit. So we just want to say that at any point, at different point of time, how many people are there inside the room actually. So if you look at this, you look at the red one here. So this top says that there are around 5 persons. And look at this. This says that there are around 3 persons. Here there are none there inside the room. So initially there was nobody inside the room, and slowly 1 person entered, 2 person entered, 3 person entered. So this is, and 5 person entered. So we find those kind of pics here where there are 5 persons inside the room, and we find there are 3 persons inside the room. I repeat, there is no camera, there is no wearable device. The persons are not wearing anything. It's only a Wi-Fi router, Wi-Fi module, that is ESP8266, which is being used inside the Wi-Fi router also. So we just collected the transmitted and received signals and then plotted it and found that okay, there is a change in the RSSI values through which you can count number of people. So that's the first thing, first kind of experiment we did. And then what happened, we started doing so we did the analysis and all these things. We found that the RSS technique is too noisy in the sense it doesn't give a lot of information to me, and it can only do certain things. So only RSSI value, if you look at this line, 1, 2, 3, 4, fourth line, only RSSI value we can detect the object or human, but not localize them. We cannot find out where are they, what are they doing, but we can find out okay, there is somebody there. So to localize the object, we need ultrasonic or radar sensors. It is not possible with only RSSI as of now. I don't know if somebody comes up with another idea and all that. So the Wi-Fi protocol, now I come to the CSI part of it. So the IEEE 802.11n, that's what is the normal Wi-Fi router protocol, uses 2.4 or 5 gigahertz frequency. And these days, mostly the routers are dual band actually, either 2.4 gigahertz band or 5 gigahertz band. And with a bandwidth of 20 to 40 megahertz. So the 2.4 uses 20 megahertz, the 5 gigahertz uses 40 megahertz, that is the bandwidth, because you can use so many communications parallelly with the different bandwidth, etc. 802.11 AC only works with 5 gigahertz. It doesn't work with 2.4 gigahertz. So what we have done is, what people are doing is that 802.11n, which is omnipresent. Almost every Wi-Fi router is according to that standard. The number of sub-carriers, we call them as the NSC. The number of sub-carriers means the sub-channels. Each channel is divided into some sub-carriers which carry the data for wireless communication, depends on the maximum bandwidth. For example, 802.11n, the CSI tool is limited to 30 sub-carriers. I repeat what I said. I said that in the 802.11 standard, there are 30 sub-carriers, 30 small channels through which the data is communicated. So 30 sub-carriers is equivalent to 30 CSF channels. So each subcarrier or each channel has a characteristic. So we get 30 characteristics for one channel. Now, okay, I come here. So the channel state information, the CSI is used to capture the fine-grained variations in the wireless channel. So it gives you a lot of information. The RSSI gives a combined aggregated value, but CSI gives you each channel-wise, subcarrier-wise value. The CSI is strength of an individual subcarrier, that is one subchannel. It contains the amplitude, it contains the phase, and it contains also for each OFDM carrier. OFDM carrier means that subchannel. So thus it is more informative than the RSSI value. The main challenge in CSI-based approach is that accessing the CSI data on a commercial device is either not possible or limited to, say for example, the desktop, what desktop we have or what laptops we have, as such they don't capture the CSI value because they are only worried about their data transmission. So many a times the chip manufacturers keep the CSI as a private feature, but people for researchers, etc., there are tools, there are MATLAB also and other things, you can capture the CSI values. Python also came out with some libraries where it can capture the CSI values. The CSI values are now recently reported that even the Raspberry Pi devices also can capture the CSI values. So there are many things are coming up slowly. So with the help of the CSI techniques, we can do more accurate localization, object tracking, and interference evaluation. That's what is the purpose here. We tried with RSSI, it has its own limitations. Then we examined what is the CSI. Then we found that it is more capable. Then we tried to see what you are doing. In fact, this is a small explanation of what happens. It is not exact explanation, but I'm trying to see an analogy that if you look at a sunbeam or a light comes, and if you put a prism there, the prism separates the bandwidth, right? So in this case also, the signal strength is coming. The OFDM will divide into some subcarrier 1 to subcarrier 3. Now each subcarrier, if you look at the color band here, each subcarrier, look at the color band here. Each subcarrier is a subchannel. Now the CSI value is a characteristics of each band here. So you get 30 such things actually. Now I don't want to go through this slide because anyway I have already told you what is the problem with the RSSI and what is the advantage of CSI, and this also gives, this slide records about all these things. Now look at the kind of a modules here. What is my input? My input here is now look at this diagram. So there is a transmitter here, and these are the receiver. There can be a desktop, there can be a smartphone, there can be another wireless device, etc. And there is a chair, there is a human being. So there are so many objects here. The transmitter will receive. Some signals will go directly, some signals will go after reflection and all these things. But all these things are recorded in the CSI value, and the CSI value consists of a lot of information about all the channels actually. Now, what is the signal processing part? In fact, I'm not talking about signal processing. There are a lot of computer science. We do a lot of noise filtering and all that. So there will be a lot of noise actually. If there is a fan running in the room, that noise will come. But there are a number of noise filter algorithms for studied over last 5 to 6 decades. So we do a noise reduction algorithm. We eliminate the noise. Then we transform the signal. People use Fourier transform, people use wavelet transform, and people who are using different transform techniques, Hilbert transform and all these things. It depends on what activity you want to measure and all these things. Then you extract the signal, the raw signal. The actual signal you extract from them. After transforming it, you can transform from time domain to frequency domain to time domain, depending on whatever you want there. Now this is the algorithm. Now the algorithm is that either you go for a learning based algorithm, people use a modeling based algorithm, people use a model, and based on that model they use it. People say that okay, what is this model actually? The model is that I have created a model for some other application and I bring it and use it here. Learning based is that okay, I will use this Wi-Fi signal for 2 days, 3 days, 4 days, 5 days, 1 month, and learn the pattern there. And some people use both actually. So there are hybrid models, there are learning based models, and there are pre-learned models which are already there. Now what are the applications? What you can do? We can have a detection, we can have recognition, and we can have estimation. Now estimation is that if the guy is here, where he will be at the next moment. So that's an estimation, a probabilistic forecast. You can recognize who is that guy, who is that person, so that is also possible. And you can detect different type of activities, whether he is jumping, whether he is running, whether he is sleeping. So these type of things we can do as an application based on the algorithm you choose. So if you look at this, that's the detailed study, and here it's a pictorial representation of all these things. So what you do, the T stands for a transmitter, R stands for a receiver, A and B, they are the some users, human beings, etc. There is a wall here. So there are so many things actually. There are so many things. So the transmitter sends a signal, the receiver receives a signal, but there are lot of things that is here. Now this A will move here, will go there, and all these things. This A is a moving object actually. So what is this NLOS? NLOS is the non-line of sight. So it is not necessary. I will also, if time permits, I will show you 2 slides there, because the Wi-Fi signal has the capability to go through the walls. So it is, say for example, if my router is across this wall, I still get the signal. So that means the signal is able to penetrate through the walls. So it doesn't stop me from monitoring a person who is inside a room without going inside the room. So that's also, and you don't have to have a Wi-Fi router inside the room also. So many people have started working on that. We are also trying very hard on that actually. Then you try to find out location, where is that person. Now the material, suppose you say that this is a wall, then whether it's a wooden wall, whether it is a cement wall. So depending on that, you have to find out the signal strength changes, the signal characteristics changes, and then you have to see that, okay, if it's a wooden wall, the person may be just 2 feet away. If it's a concrete wall, the person may be 1 foot away. So that's how it is. Now what you do, what is the sensing of this? You detect that there is somebody, you detect where it is, that is what, where is that human being, and then you detect the behavior, whether he is sitting or walking. So these are the sensing part of the human being using the Wi-Fi signal, even in presence of non-line of sight. So that's a beauty, and that's a important of this. So what you did in the experimental setup here, the experimental setup of human activity detection is that the data set that contains CSI values. What is the CSI value? CSI value stands for channel state information. It comes in every frame, it comes 30 such channels are there. So 30 channels are there, and we collect this, the data is collected. I mean, we didn't collect, the data is collected for 6 activities. Somebody was walking, somebody is jumping, somebody has fallen down, somebody has clapping, sitting, and waving his hand. Now these are the 6 activities. So how do we collect the data, or how the data is collected? This is basically you try to set the experiment, and then ask a student or you yourself that go and perform this activities again and again. So the experiments are conducted. The data here is reported that the experiments are conducted for 8 days. Sorry, with 9 participants. So there is only not 1 participant, there are 9 participants, and the data is collected for 8 days. And each activity is collected for 5 seconds. So 5 seconds you collect the data and then do it. Now the data is recorded for 50 times. So each activity is done for 50 times actually. So if I'm walking, the data is collected 50 times. I walk 50 times, and then the data is collected. So that average can be done. So next what happens? So the data was recorded for 50 trails, means 50 instances of each activity, and each trail is done for 5 seconds. So if I have to jump, I just jump once, that takes 5 seconds. So every activity, so I say 1, 2, or I mean the data is collected like this, you say 1, 2, 3, go. So the person will start walking, and you collect the signals. Similarly for the other thing. So you use Raspberry Pi devices, you use OpenCSI platform is also there. So communication was done with a 2.4 gigahertz frequency. 2.4 gigahertz is a standard Wi-Fi router. The transmitter and receivers are placed at a distance of 2.5 meters. So 2.5 meters is equivalent to almost around 8 feet. So 8 feet distance. So in a small lab, there are 8 feet distance. In the 8 feet distance, you conduct this experiment. Now you look at this actually. So you on the right side, if you look at this side, this is a Wi-Fi router. In this side, this is a desktop. To the desktop, this is attached actually. So there are 3 receivers here, 3 antennas actually. Antenna number 1, antenna number 2, antenna number 3. There are also 3 here. 1, 2, 3. So 3 transmitter antennas, 3 receiver antennas. And how it looks like? I mean, this is a standard card actually. This is Intel, I think N5500. So Intel N5500 module. This module is there. This is fitted inside this desktop. So this you take. So this is a receiver which receives the Wi-Fi signals. This is the standard Wi-Fi router. You put it inside your. In fact, without this also you can get the signal. But I want 3 receiver antennas actually. So how many things here? Transmitter 1, transmitter 2, transmitter 3, receiver 1, receiver 2, receiver 3. Now, how do you measure the signal? We measure the signal from transmitter 1 to receiver 1, so 1 cross 1. Transmitter 1 to receiver 2, 1 cross 2. Transmitter 1 to receiver 3, 1 cross 3. Similarly, for 2 cross 1, 2 cross 2, 2 cross 3. 3 cross 1, 3 cross 2, 3 cross 3. So 3 transmitters, 3 receivers. So 3 into 3, there are 9 pairs actually. In each pair, there are 30 subcarriers. That's what I told you. So 30 into 9, there are 270 CSI values I collect per frame. For each frame, I collect this data. So how many channels are there? Sub-channels are there? 30. How many transmitter receiver pairs are there? 3 transmitters, 3 receivers. So 3 into 3, 9 multiplied by 30. That is 270 CSI values I get per frame. And in 5 seconds time, I get around 100 frames. So 100 into 30 into 3 into 3. That's the data we get. So 100 into 270. That's the size of the matrix. So let me explain all these things. So we observed that each activity is behaving abnormal when compared to other activities at some point of time or at some particular subcarrier. Now that's very important actually. First we try to see that how this behavior is changing. Now activity is doing nothing. That means you don't do anything. Sit down still and don't do anything. So that is considered as the reference. That's considered as the null activity. That's considered as the ground truth. Now the data is obtained in for the, as I told you, 100 frames. In 5 seconds, I get 100 frames, 30 sub-channels. For each sub-channel is there. 3 into 3 is 3 transmitters and 3 receivers. So all the graphs, I mean, there are a few graphs that are coming up in the next slides, are plotted amplitude versus the total number of frames. Now look at this. Only amplitude we plotted because I want to show you that. Now, first we wanted to study actually how it looks like and all these things. Now look at 5. What is channel 5? There are 30 channels. So in the channel 5, we found that stream 1 cross 1 means transmitter number 1, receiver number 1. Now the guy is falling down. The subject of experiment is falling down. If the subject of experiment is falling down, look at the x-axis. The x-axis says that 0 to 100 frames. And this is the amplitude actually. On the y-axis, this is the amplitude. Now when somebody falls down, look at this. Even if I say it is 5 seconds, the falling down happens only at an instance. So at around 50th frame, in this frame, you see that the red line, I don't know whether you see it as a red or a magnet. The red curve here, is the ground truth, no activity. And when the person is trying to fall down, that means you say 1, 2, 3, fall down. It takes a second and then falls down, etc. Right? So that means around 2 seconds or something, it finds that there is a peak in this particular channel number and at this particular combination, transmitter 1 and receiver 1. The same thing is also observed. Similar thing is also observed in other streams, but this is very prominent actually. So if you can measure this, if you can see this, you can immediately say that somebody has fallen because of these characteristics. Similarly, we looked at jump event. Now in a jump event, like you don't jump and come back, that guy started jumping a little bit. So we found that the jump event at channel number 10, remember there are 30 channels. So at channel number 10, the same string, 1 cross 1 means transmitter 1 and receiver 1. And what is transmitter and receiver? There are 3 transmitters and there are 3 receiver antennas. 1 cross 1 means transmitter 1 to receiver 1. Jump activity at channel number 10 is characterized like this. So there is a clear, the whole purpose is that there is a clear indication that the Wi-Fi signal changes with respect to the activities, and that you have to very closely observe. So first we try to plot different graphs and see that whether there is a change. If there is a change, how the change looks like and all that. So this is a activity called walk. Now look at this. When you are walking, there is a series of changes actually, because it's not instantaneous. Like jump is instantaneous, fall down is instantaneous, but walking there is a series of change. Look at the blue line here. There is a continuously change corresponding to the ground truth or no activity. So you say that this guy is walking. Similarly, for clapping, waving the hand, and there are certain activities which are not very clear actually. For example, waving the hand, there is a change, but if you look at this is clapping and this is waving the hand. Now this is a visualization actually. I collected the data, plotted it, and looked at different possibilities and tried to find out that how it looks like, whether there is a change or not. But we cannot have a person sitting there to look at the changes and try to see that. So we have to develop algorithms for that. What we did, I think I went through the couple of sessions in the last 2 days. So there are people talked about deep learning, LSTM and all that. So I don't want to go into the technical details of that. I expect that you have understood or you will read on your own. So first we tried to implement with LSTM. LSTM, it's a deep learning technique again, long short-term memory. It's a very popular application for time series data. We thought that can we try to do it? So what we did at the first step, so for example, I said 5 seconds I collected 100 frames, but this 1, 2, 3 go. So it takes a few milliseconds for the person to be active. And after that, what I did, I trimmed the frames actually. I removed the first 10 frames and removed the last 10 frames. And so instead of 100 into 30 into 3 into 3, we considered 80 into 30 into 3 into 3. So we took all the CSI values. But unfortunately, the accuracy value is only 20%. We didn't get good accuracy. not at all good accuracy. 20% is not acceptable. That's a random number actually, anything you can say. So we didn't get anything. So LSTM is considered to be a failure in this case. LSTM after applying PCA. PCA stands for Principal Component Analysis. So what we did, we thought that, okay, this 270 values do not give anything actually, this 30 into 30 into 3. So we applied a PCA, Principal Component Analysis, and we found that, okay, we'll take top 70 CSI values, which top 70 features, and then apply LSTM value. Accuracy was only 56%. So it was also not that good actually. Then we applied PSA with the 30 features, accuracy came down to 50%. Somehow we struggled, we cannot go even beyond 60% at any point of time. So we thought, okay, LSTM is not a good option, let's try something else. Then what we did, we went for a convolutional neural network. I think yesterday the speaker was also talking about that, CNN implementation. So we went for a convolutional neural network. What I mean by this, all activities combined, we collected the data for all the data was collected, not we. The data was collected for all activities. What are the all activities? Jumping, walking, falling, sitting, waving. So all activities are combined, and we say that, okay, this is for jumping. So we tagged them, we leveled them. Once we leveled them, and then we started training using a convolutional neural network with 15 layers, layer 1, layer 2, layer 3, 15 layers. So you know that input layer, output layer, and there are 13 input hidden layers in this CNN. So we used 15 layers of CNN and fine-tuned the parameters for better accuracy. We tried with different type of parameters, etc. The training time was high because, you know, there are a lot of data actually, right? We have 9 participants. For each activity, there are 50 instances. So there are a lot of data. So the training time was, of course, it was high. So it took almost 40 minutes to train the data for recognizing the activities. So we tried to reduce the time at the cost of accuracy also. So that's a different thing. That's a typically, Tinku Acharya says that it's a typical research paper activity. So I will not go into that details. We'll come up to the, so we tried for accuracy, etc. Now look at some of the results here. Results of CNN algorithm. CNN means this convolutional neural network algorithm with 15 layers and the captured CSI values. What are the CSI values? 30 frames, 3 cross 3, and 80 frames. So 80 cross 270 values. So we gave all these things with 15 layers. It got thing. So what you do, we got an accuracy of, if you look at the result here, 93.94%. And look at the laser pointer here, 93.94%. That means 93.9 means almost 94%. 94% of the time it is able to train itself for correctly recognizing jump as a jump, walking as a walking, sitting as a sitting, falling as a falling. Now the error rate also, so this side, the x-axis is actually iteration. We tried for 500 iterations, 1000 iterations, etc. And we found that, okay, reasonably 94% accuracy is coming for CNN algorithm. Now what we do, I'll also tell you here. I'll just drink a sip of water, just a minute. So this is for the total data actually, 80 cross 270. It takes sometimes it takes 40 minutes, sometimes it takes 80 minutes. So we thought, okay, do we need all these 270 CSI features, or can we try with reduced features actually? So can we take out some of the CSI values which are not important? So we applied principal component analysis algorithm, and we took only five CSI values out of all the 270 CSI values. But you know, the accuracy came down to almost 40%. Sorry, not 40%, it is 54%, 53.63%, etc. But you know, this is instantaneous. I mean, I don't have to tell that how much time it takes. It just gets trained within not even seconds actually. So take only 5 CSI values instead of 270 CSI values. The accuracy is 54%, but this is exact. I mean, this is almost real time. We tried with 50 PCA values instead of 270. We tried with 50 PCA values. The accuracy was almost 75%. If you look at this is 75% here. So what is the idea here, or what is that I'm trying to present here? Is that you take all the data, the raw data, clean data, and then you try to learn it. When you learn it with all the data available with you, that is 100 cross 270, and for each, that is one frame. One activity, there are 50 such activities there are 6 such activities. For each activity there are 50 such instances and 9 days. So this is the volume of data in terms of GB. So we tried, no, it should be very fast and all these things. So we tried different options, but then the different options has its own limitations. It doesn't give me better accuracy. If you take the whole data, it takes time, but accuracy is almost 94%. Now the problem is that we thought that okay, what is my requirement? My requirement is that suppose I want to see that look, my grandparent is there. My grandparent is going into the restroom, and I want to monitor in the restroom whether he or she has fallen down or not. I don't want to monitor whether he is waving his hand. I don't want to monitor whether he is jumping there, because anyway he or she will not jump at the old age. I don't want to say whether he has slept there or not. So these are the things we don't want. I just want to monitor whether my grandparent or my grandfather or my grandmother or my father or mother has fallen down inside the room or not. So we thought that I have only one activity to monitor, because this is what is required. So if I have to monitor one activity, let's say the fall only, I don't care about the other activities. So I take all the data, but I want to maximize the fall activity only. Similarly, I want to maximize the jump activity. Suppose my kid is there inside a room, and I want to see that whether this fellow is jumping or not. If it is jumping, I want to capture it. Falling, we want to capture it. We don't want to capture about walking, running, and all these things. So some of these experiments, from this data, we wanted to say that instead of capturing or recognizing all the activities, can you try to maximize one particular activity or two activities? So in that case, so experimental results for recognizing individual activities. So we trained the whole network without validation. We didn't do any validation. We just tested it, and then tested for each activity separately using a program. So we considered 100 instances of each activity for testing. So what we did, let's say I have 1,000 such records, 1,000 records for falling, 1,000 records for jumping, 1,000 records for clapping, 1,000 records for walking. Then out of the 1,000 records, I considered only 900 records for training. Rest 100 records on randomly I picked out, and I wanted to use it for the testing. What is that I get? So what we did actually, if you look at the right side of this side, this is the total data set. I took 80 frames, 270, and this is for each activity, each person, each activity. This type of data are there for each one is for 50, and there are 9 such participants. So we have a lot of data actually. Now, and this is for 50 cross 49 because we wanted it to be a little faster. So if you take the whole data set, the falling activity is recognized with an accuracy of 98%. Now, what is the difference between 94% and 98% here? 94% is the overall accuracy. Overall accuracy means taking all activities together and to try to see that whether this falling activity, walking activity. So you will try to recognize every type of activity. Now we changed our model. We said that okay, we are not trying to interested in every type of activity. I am only interested in one activity, whether we are able to detect it or not. Data is there for all activities, but I want to find out for one activity. I want to maximize that. I want to detect if my kid has fallen down or not inside the room, or my mother or my grandmother has fallen down inside the restroom or not. If this is to be done, then we found that almost up to 98% accuracy. I think the previous speaker told that 100% accuracy is almost a dream. It's not possible. But even without camera, now remember, there is no camera. Okay, there is no camera. There is no wearable device, there is no accelerometer sensor, there is nothing there, nobody is there. Only thing is that your home Wi-Fi router system is there and there is a receiver. So we found that falling is a very distinct activity. We can recognize with 98% activity, and almost all activities we can measure with a percentage of almost 95%. Only waving is a very small activity, and that is not able to, we are not able to capture it more than 92%. But if you want to faster, suppose I want to do it within no, imagine faster in the sense the recognition is always faster, the training time. Suppose I want to install it and somebody comes to my home, takes some configuration and I have to install it, and you want to install it within 5 minutes or 10 minutes and go. If you give me a day, this will be the rate. But if you give me 5 minutes or 10 minutes, probably this is the accuracy. 85% time you are able to recognize whether it is falling or not, and something like that. So the whole idea is, I think I'll just stop in 2 minutes. I have 2 minutes time, right? Hello?
Yeah, you can continue. Whatever, okay. I mean, there is no constraint of time.
Okay. So this is what I wanted to talk about, this human activity recognition using Wi-Fi sensing without using traditional sensors actually. Now, by the way, I said that there is a possibility that the same sensing mechanism, the same Wi-Fi router, etc., there is nothing inside the room across the wall actually. So people call it as a through walls Wi-Fi sensing. Through wall in the sense across the wall. You are behind the wall and some activity is happening across the wall, and you have to, can we do a kind of a sensing there? Again, I tell you, repeat it, there is no camera, there is no wearable sensors, there is nothing in the body, etc. The guy is moving around happily. So if you look at this, the idea here is that look at, there is a Wi-Fi router here, and it sends a signal. Even if there is a wall here in your home, look at the Wi-Fi signal will go, hit the body, and some will again pass through the body, and then some will come back. Okay. Now look at this. The signal strength, actually, it goes with a bit of signal, goes through the wall, hits the body, again goes through it, but then some of them comes back, passes through the wall, and then come back to this. So if this router is a transmitter as well as a receiver, because they are known as transceivers also, it will try to detect that, okay, there is something goes, again I go back. Okay. Now look at the signal strength here. There's a lot of signal strength here. Then you go, it passes through the wall, hits the body, some part will pass through, and then after hitting body, it will come back. Now, when it comes back, look at the signal strength. It is very, very reduced. Very minimal signal strength will be there. But people have still worked on it, tried to find out what is the signal strength here, and then try to predict what is happening inside this here. Now, what happens actually? This is the wall reflection. Look, the signal, when it goes through it, from the wall also it will reflect, but the wall reflection is too huge. And the wall reflection is almost 10,000 times stronger than the reflections coming from the null line of sight. So the challenge to the communication engineering and electronics people is that, how do you remove this huge noise? In fact, what people have done is a smart move. Usually what happens, the signal is more and the noise is less. All the noise filtering algorithms, they actually filter the noise, assuming that the noise part is less, the signal is more strong, the noise is weak. What here people have done smartly, that they assume that they interchange the role actually. They consider noise as the signal and signal as the noise. So the signal becomes feeble. So the noise filtering algorithm, what they used to do, they filter the noise and keep the signal. Here they filter the noise, but that noise is actually the signal. So they keep the noise part of it, filter the signal. So the signal that is coming out of the wall and other things are filtered out as a strong signal, and the weak signal is captured actually. So after that, they try to track people from the reflections and all these things. In fact, this is not our work actually. We have not done anything here, but I'm just following some others' work. So what they do, there are two simple gestures to represent a bit 0 and 1. Our communication is based on 0 and 1 only. What you do, suppose you say you can combine a sequence of gestures to convey a longer message. Suppose I'm inside this room, I cannot speak and other things. I want to, through my walk, I want to convey a message. So if I move forward, let's say it is 0. If I move forward, let's say it is 1. Sorry, if I move forward, let's say it is 0. If I move backward, let's say it is 1. So I'm standing inside this room and nobody is watching me. Somebody there outside, across the wall, and I want to send a message by just moving forward or moving backward. Just a simple experiment. So bit 0 means step forward followed by step backward. Bit 1 means step backward followed by step forward. So you come back and move forward, that's 1. You move forward and then come back, that's 0. So what happens actually, again I repeat, it's not our work, I'm just copying from some other's work. So if you look at this parameter, like you just measure it and plot it as a heat map. This is you are moving forward. If you move forward, actually the signal strength will be little more on the other side of the wall. If you move backward, the signal strength will come down. And then this is move forward and then backward. So this is 1. And then this part, move backward and then move forward. This is 0. Sorry, this is move step backward, and then step forward. This is 1. Move forward, step forward, and then move backward. This is 0. So this is 0, 1. This entire pattern is 0, 1. So step forward is this, step forward is this, step backward is this, step backward is this. Now what you are doing, you are just sending a signal. So this is an encoded signal with gesture, without camera, without anything. So what you do is a simple filter actually. I don't want to go this. So bit 0, bit 1. So I'm sending an information called bit 0 and bit 1. So the gesture interface that works with null line of sight. Again, I repeat, null line of sight means that you are not visible. You are not in the line of sight, but still you should be able to find out what is happening. So for example, inside the restroom or inside a particular room or what is happening there, and you want to monitor without a camera and without any wearable device. So what I want to conclude here is that we try to present a model which is called sensing without sensors using Wi-Fi signals. We kind of presented or tried to tell that the RSSI and CSI parameters can be used to model the problem. The preliminary experimentation, I repeat, preliminary experimentation, it is not a full-fledged experimentation. The preliminary experimentation results to count the number of persons and basic activity detection and gestures is possible. We are still struggling. We are still trying to figure out how do we fine-tune the activities. Can we say, some people say that when I'm typing in a keyboard, so that also should be what is that I'm typing. So if you can do the signal processing and training to a minor level and lot of training and all that, even you can do some kind of a small things, right? Your finger movements, your heartbeat actually. When your heartbeat means you compress, you suppress, you expand and you compress. So this also changes the CSI pattern of the Wi-Fi signal, and from that also you can measure how many times I'm breathing inside the room. So people say that they are able to breathe breathe a baby from another room, not sleeping in that room actually, using the Wi-Fi signal and all that. So thank you. And before I conclude, I must acknowledge two of my students, Ajit Sahu and Shruti Panmaster. They have been doing this work, and they are my PhD students. And thank you very much. Thanks for your patience.
Thank you for your presentation, sir. So now we'll go for the questions.
Yeah,
so
please.
first question, let me take one. Which are the sensors used in electronic nose of olfaction system, olfactory system?
Which system?
Which are the sensors used in electronic nose of olfactory systems?
Olfaction system.
Olfaction system.
Well, I have no, but let me say electronic nose is basically gas sensors.
Oh, the one who senses smell.
Smells actually. So the methane gas sensor is there. So for example, people are using it for detecting the spoilage of a food, right? If a food is spoiled, then the smell is different. So they use methane, and the spoiled food actually generates a lot of methane gas and all that. So all these things are gas sensors actually. So, but I'm sorry if I'm not able to answer it correctly, because the sensors which used, I don't want to tell the exact model number in QTT1 or something like that, but these sensors are used for basically detecting the gas, detecting sulfur, cooking gas, gas leakage, right? So there are sensors to detect gas leakage. That's also a part of electronic nose. In fact, electronic nose is a series of sensors actually, different type of gases, different type of content, including temperature and humidity. So all these things taken as a series, they call it as an electronic nose. But they are basically gas sensors. So you Google gas sensor and you find a lot of sensors there.
So one more question. In the case of through wall sensing, weak signal is received. How will it be used for inference?
See, that's what I told you. In case of a through wall sensing, the noise is dominant than the signal. That is true. Now, what people have done smartly that in case of a normal noise filtering algorithm, they filter the noise and keep the signal, assuming that the noise is less and the noise is weak and the signal is stronger. But here, the noise part, they consider that the reflected signal is the actual signal, and the noise is too much actually. So they are not able to remove the big noise or the strong noise. What they did is they removed the small signal, which they considered as a noise, and that removing of the small signal, they captured it, and then they tried to characterize it. Again, what I said is that in any noise filtering algorithm, noise is considered to be weak and the signal is considered to be strong. So when they apply the algorithm, the weak part will be cancelled and the strong part will be retained. Here what they do is partly that when they are trying to remove the weak part, they didn't remove the weak part, they contained the weak part and removed the strong part.
Okay.
That's it.
Okay, sir. How can we classify RSSI and CSI signals?
Classification is normally, for example, normal classification algorithms. You take this as a data, right? So RSSI is a data, but RSSI problem is that it's a single value. So for every time stamp, you get a single value. But for CSI, as I told you, for every time stamp, I get 3 cross 3 cross 30. So I get 270 CSI values for every time stamp. Every instance, I get 270 CSI values. But corresponding to that, I get only one RSSI value. So RSSI value doesn't give me enough information to detect different type of activity, but some coarse grain activities, some minor activities can come. For example, whether there is a person or not, that can be detected using RSSI. But you cannot detect what is happening or what is he or she doing there.
And next question, in which software did you monitor the real-time Wi-Fi router signals?
Okay. There are, so for example, the graphs and all these things, you see it in the MATLAB actually, or in Python. there are this. If you go to this, even they are there in GitHub and all that. You go to you how to capture. If you have a N5300 card installed in your system, and you use that in GitHub code and other things, you can capture that. And the file name is pcap file, PCAP, P capture. CAP stands for capture. So pcap.pcap, you get a file name, let's say file1.pcap. So that pcap file is a complex file actually. Complex file in the sense it is consisting of complex numbers, because it consists of amplitude, it also consists of phase. So it gives a complex number. That complex number x plus iy. So x part has to be separated, y part has to be separated. But for that you have MATLAB codes and all that to read the pcap file. Even you have Python code also to read the pcap file. Reading is not important. You read them and then get the CSI values, and then what do you do? Because there are a lot of information, and these are all numbers: 23.345, 6.982. So these are so many numbers, and these numbers have to be grouped into, and then we have done some training and all that.
Then next question, if multiple Wi-Fi transceivers are present in a particular area, will it create more noise?
Of course, yes. Of course, yes. It will definitely create more noise. But you have, that's what I said. During the training, you have to say exactly where is the, that's what I said. During the experimentation, they say that where is the position of the transmitter, where is the position of the receiver, what is the distance between the transmitter and receiver, what is the configuration of the room. Because you see, if it is small room, the reflection will be very high. If it's a large room, the reflection will be very low. So we have to do it. That's what I said. The ground truth or the null activity, first the null activity has to be trained. Once the null activity is trained, then we start training with the other activities. Okay. And if there are two, that's what I said. Here also there are three transmitter antennas and 3 receivers. So we consider it as a 3x3. Now suppose you have 2 Wi-Fi transmitters with 3 antennas each, that becomes 6x3.
Right.
Right.
So is reflection pattern is different for human and a dog?
Experiment says it is different, because the way they move and all these things, the experiment says that they are different. In fact, people are trying to see that there is somebody hidden inside the room, right? You are not able to see, but there will be a reflection pattern actually. If you have trained the null activity correctly, if somebody is hidden also, there will be a reflection from that actually, because the Wi-Fi signals are 360 degree. It goes in every direction. If somebody is hidden inside behind an almirah or something, if the signal reaches there will be a change in the reflection pattern. That also people have studied how to find out somebody who is hidden inside a room or hidden in within a bed or something like that.
Can it be used for paranormal activities?
What is that paranormal activity?
Something like that.
I mean, when they are calling some spirit.
Ghost.
Yeah.
No, I'm not able to hear you.
When someone is calling the spirit, ghost.
Paranormal activity. Paranormal activity.
I don't know.
Yeah, paranormal.
No idea. No idea.
So is Wi-Fi safe for health, specifically during pregnancy? It's a good question.
That debate is on. There is no conclusive evidence that it is good for health or bad for health. But all said and done, it is there. You can't help it. Whether you like it or not, it is already there. But that's what I'm saying. When people you want me to wear it in your waist or something, people have reservations. But suppose, say, for example, they say no, signal will be there. It will go to my baby and all that. But if it is there in my room, it is already there. I mean, I'm used to it. So there may be issues. There are issues. There are some people have already said that there are issues. Some people are saying that there are no issues. But I tell you, every technology or every medicine comes with some kind of a side effect. And if you have to say, I very recently I was listening to a video. They say that some 500, 600 or some 1,000 years back, or maybe a little more than that, some 3,000 years back or million years back, there was no disease actually. People were dying out of because of aging, but people are not suffering from disease. Disease comes because of pollution. Pollution comes because of industry. Industry comes because of requirement, employment, and all that, right? So there is a chicken and egg problem. You have to get this, and you have to find out that what is the benefit compared to what is that loss you are getting. There is no such conclusive proof that yes, it is affecting, but also it's like NP problem, right? NP heart problem. You have no conclusive proof that it is a non-polynomial or it is polynomial.
Thank you so much, sir. It was really a wonderful and insightful presentation. and it's a very novel idea. I think many of the participants today, they have taken a lot of ideas, innovative ideas from you, so they can just try to start their work or try to implement in their own research work. So, sir, definitely we will take help from you in this area, because many of my students are also working in this, not exactly, but related to this field. So, in future, we will take help from you. And thank you for your time.
Madam, 1 minute. Sorry to interrupt. There is one question which is asked by Dr. Tapun Kumar Patnaik. Can this system work under C?
C
Under?
programming.
No, under C.
Under sea
Samandra.
water. Sea water. Okay.
Underwater, right? Underwater. Underwater sensor.
Yeah.
Yeah.
I tell you, when it works with wall, it should also work with underwater sensor. But as I tell you, these are very recent work actually. I mean, people have started working in 2018, 2019, etc. Lot of work has to be done. Lot of experimentation has to be done. It should work. My intuition says it will work, but I have not seen any literature so far that people have done it in underwater and all that.
And so lastly, it is a very informative session for us. Thank you.
Okay. Thank you very much. Thank you very much.
Thank you, Professor Udgata. Thank you, sir.
Thank you. I'm leaving the room meeting, madam.
Okay, sure, sir.
Okay. Thank you, man. Thank you, everybody. Thank you, everybody.
Thank
Bye
you.
bye.
Thank you, sir.
So we have another session that will start from 1 o'clock. So till then, we are free. Now you can then immediately come back for the third session. And the third session, Young, he will speak on a topic which is quite relevant. That is deep learning in medical image processing. Deep learning in medical image processing, and the speaker is Dr. Anand Nair from Vietnam. So he will speak on this topic, and nowadays medical healthcare area is so demanding, and lot of innovative softwares are coming up how to strengthen this particular area. So definitely today we will get a lot of ideas as well as information from Dr. Nair. So let's so let's come back at 1 o'clock, assemble here to listen to him. Thank you all.